thank you to the organizers for giving me the opportunity to come back here. So I spent exactly, as many of you, several months here, and it was a great experience, both mathematically and for living here. So the also apologize in advance. I will have a little bit sore throat, so coughing from time to time. So the topic is the following problem. So I'll restrict because you can ask different questions. So, and so it's like when Raphael mentioned in his talk that it's a problem, which is why we gather here. And but we offer many different kinds of methods and ideas for dealing with this problem. And so this will be a Hamiltonian system. In 2.5 degree freedom, and in Marian and Jean-Pierre's talk, they were dealing with the autonomous system of 3 degree freedom, which is almost recurrent. So so the question is global instability. So a little bit history, as even if everyone already knows. So this was first studied by John Mather, and who basically formulated the theorem for the global instability, and also gave part of the proof, but who unfortunately didn't finish. So there are many other ideas to study this problem, including Jean-Pierre and Marianne, and also with a great tradition of ideas coming from a priori stable system with Raphael, Terra, Amadeo, and so all of us have been involved to some degree for this problem. So I think so. What I would like to do is focus on the approach to this problem, which has been a little bit different from much of the talks here, which is to study this in the variational sense, and to give the simplest way to describe, in a sense, the method, but also includes the difficulty, the main difficulties of the problem. What I'm actually going to do is I'm going to focus on the simpler problem, the following model. Sorry, equal to 1/2 p squared. So far, this is the famous, the first part, before the perturbation of the famous Arnold's example. And I would like to consider a perturbation of this type. And I would like to study the family of Hamiltonians where, let's say, so for the C2 norm of R is less than 1, the system itself will be smoother than this. But for the norm estimate, we would only need C2. And delta is sufficiently small, but fixed. And I would like to study the whole range of parameters, epsilon between 0 to epsilon 0. So it's it's a little bit different from the a priori unstable system, because I like to call this a singular perturbation. So what you like to say is that the remainder term is small enough compared to the first term, but you would like to take these two terms simultaneously to 0 as epsilon go to 0. So this causes various problems for the study. But the main idea I would like to drive to is actually the variational problem has the benefit of somehow do not require that much about the system. So at the end of the talk, I will formulate some condition which is not only satisfied for this system, but also satisfied for other systems which may come up in double resonance. And in fact, then we can basically patch everything together using the same method. And so that will be the goal of this talk. But at least let me state the theorem. So the theorem, this is so it says for a residual. Okay, let me first let gamma be the following subset in R2. Let's say C2 is in 0, 1. So, but you can do it for any finite neighborhood, and this is a subset of R2, and this set corresponds to the number of potential p's for which the speed of theta 1 is equal to 0. So this is the resonance. Then there exists a residual set of RC2 less than 1 such that for any C1, C2 in gamma, there exists an orbit theta p t such that p of let's say p of 0 is equal to C1, p of t is equal to C2. So as usual, you can also prescribe how the orbit goes. So for example, you can fix several c's, but in that case, I'm not sure you can hit precisely the point. So so never mind this part. So usually you would say take a neighborhood of C1 and take a neighborhood of C2, then you can go from C1 to C2. But some peculiar benefit of our method is that you can hit precisely a value if you just fix the starting point and end point. I'm not sure about the intermediate points.
So
yes.
What about this gamma is 0 C2? Such that C2 belongs to this? Or
Yeah, sorry.
and
Thank
this
you.
Included
Yep.
in what? In
In R2, yeah, sorry. Somehow the 2 went to the wrong place. So this is a resonant arc. So it's a resonant arc for the space. So so I would like to explain how to what is the approach to prove the statement. And so the main idea of the proof is to first you look at these are compact invariant subsets. Let me also fix some setting. So I would like to fix of the time one map phi. So I will always be looking at discrete settings. So it's a four-dimensional it's a symplectic map of the four-dimensional manifolds, and these sets called the Aubrey set exists for any C in R2. So the way I like to see it is that once you have this Hamiltonian system, then in the entire phase space you have a family of invariant sets which are indexed by C. And for this particular model, C is almost equal to the value of P, which means that you already have a family of invariant sets which almost equidistribute your action space. But they are invariant sets, they stay to themselves. So in order to find the global instability, you would like to see whether one set can be connected to the other, probably by heteroclinic connections. So the next step is to look at the heteroclinic connections. But these things tend to be hard to study. But luckily, just like in the geometrical setting, it often reduces to study homoclinic connections, which is much easier to study. So the idea is that once you get some information about the homoclinic connections, then these naturally give you ideas about which other invariant sets you can connect to. So properties of the homoclinic connections tell you which other Aubrey sets you can connect to. So then the idea is to study this, the whole picture in the phase space. So, so I would still like to just to state the definition of these invariant sets we were studying. So the invariant sets are called Aubrey sets. So actually, they are defined by mother. So my understanding. So just a little bit of a terminology for the twist map, and so these invariant sets are discovered independently by Aubrey and mother, and so that's why it's always usually called Aubrey mother sets or Aubrey mother theory for the whole theory. But as far as I know, the higher dimensional version is defined completely by mother. Because there's a smaller set which is named mother set, therefore the set is named Aubrey sets. So on that note, I will actually use the word Aubrey mother set strictly only for the case associated to twist map. So when I say Aubrey set, it means for general Hamiltonian system, and Aubrey mother set, it means for twist maps. So this is related. So these basically are invariant sets that are produced by action minimizing methods. So you first switch to the Lagrangian, which is the Legendre dual of your Hamiltonian. Then what you would like to do is you would like to look at, first of all, what's the minimum action of going from one point to another point, and this is called the Pi's barrier. I think still mother's notation. So basically, you start from point x, another point y, and what you would like to do is you would like to look at the minimum action of going from here to here. Okay, so let me just put in the parameter. So I mentioned before that these invariant sets has a parameter, which is C in R2 is identified with the cohomology of the space. So it's the inf of t goes to infinity, and here you take the inf over theta of 0 equal to x, theta of t equal to y. So the idea is that you would like to look at the action of going from x to y, and you would like to look at what's the infinite time of action of going from here to there. And the main point is that you have to compensate it, because otherwise you don't get a finite number. And this is called the Magnier's critical value. And for the classical Arnold example, you can always take f of c equal to 1/2 c squared, because what happens is basically this is what's needed to complete the square, 1/2 v squared minus c dot v. Then you just add this to complete the square. So this is the minimum action of going from one point to another. Then the idea is to produce these invariant sets Aubrey set, and it suffices to look at longer and longer curve which minimize the action but go back to itself. So the definition of Aubrey set, here I'm going to be a little bit specific, so I will index the Hamiltonian and the cohomology class. Then this will be the set of X such that the infinite time action of going from a point X to itself is 0. And this is actually necessarily the minimum, because if the action is negative, then you can keep repeating it, and the action will be negative infinity. So the minimum of the action is necessarily non-negative. And therefore, if something hits action 0, then it has to be minimum. So then this naturally lifts to a, so this is in T2. So basically, it's a little bit roundabout. So any minimizer will have to be a Lagrangian orbit, and then you take because then you take the time 0 section, then you get the invariant set for your map. So you get your Aubrey set. So coming back to that particular example, so what you have is that you have the standard picture. Here you have theta 2 and t. Oh, actually, since I'm doing time 1 map, there's no theta 2. So here is a pendulum. Yeah, this is theta 1 p1, theta 2 p2. Then the Aubrey set is simply one of these levels. So so what I would like to do is draw the connection to the geometrical picture. So far we had a very similar picture from what we had in the other talks. So here we have the invariant set. We have a normally hyperbolic invariant cylinder, and on which you have a invariant curve. And you can also find its stable and unstable manifold, but I would like to define it in a slightly different way. So stable, unstable manifold. So what you would like to do is actually you would like to look at something that's on the Aubrey set. So a bit of notation: when there's tilde is in the space T2 times R2, when there's no tilde is in T2. And what you would like to do is you would like to take any point X, and you would like to look at the backward asymptotic orbit to this to the set, and you would like to take the one that has the smallest action. And phrased in the variational method, it happens to be the following function. So there's a function called S minus X, which is simply the Pios barrier at C of zeta to X. Here, zeta is an arbitrary point in your Aubrey set. Then what you get is that you get action of backward infinite orbit asymptotic to the Aubrey set. And similarly, you define S plus X is HCX zeta. So in principle, this depends on zeta. But let me cheat a little bit and say not to worry about it. So generically, it doesn't depend on zeta up to a constant, and so that will be the case I apply it to. So what happens with the connection to the geometrical picture is the following statement. So if you have the graph of the gradient of S minus, then it actually happen to include the local unstable manifold of the Aubrey set. So let me actually index this by C. And the graph of the gradient of S plus includes the local stable manifold. So we're back to the geometrical picture we are familiar. You have some normally hyperbolic, you have an unstable manifold, you have stable manifold. And you would like to look at, since I would like to look at homoclinic connections, then I would like to look at the intersection of a stable and unstable manifold. Here comes a some benefit of the aberrational method. The benefit is the following. So you are always guaranteed to have homoclinic connections to the Aubrey set, even if you don't have a good picture of how much the stable unstable, how the stable unstable manifold intersect. So you're guaranteed they always intersect somewhere, and this is due to the minimization property. So the remark is that gradient of S plus minus always intersect at the point which is the point which achieves the following minimum. So I'll use the notation argument. So if you take the difference of this function, then you happen to always find the intersection of these two sets. So you always get the intersection of stable and unstable manifolds. Yes?
Your inclusion is in the generic case. This contains the stable. Is it always?
In this particular example, yes. So yeah, it's not always if is normally hyperbolic and satisfies certain conditions, which I will state later, then this is always true. So, and also let me just be careful. Yeah. So this is what I think I need a minus sign here. So because I'm taking the difference of these two. So. But this is actually trivial because what happens is that you have so this is the theta space, theta 1 space. So you have unstable manifold and you have stable manifold, and they intersect actually at the invariant set. So what happens is that this doesn't give me anything new. It just gives me back my Aubrey set. But the trick is because I want to look at minimizing things. The trick is to take a double cover, which is the following symplectic coordinate change. Which doubles the theta 1 and keep the theta 2p2. But then you need to make it symplectic by dividing p by 2. So then what you do is you consider the set, the Hamiltonian H composed with C, and also you consider the cohomology, which is the push forward of C. But in this case, it's simply dividing P1 by 2. So, sorry. Oh, this is correct, yes. And in this case, it actually doesn't change because the P1 component is equal to 0. So, by making the double cover, what you get is that you get the two different copies of the Aubrey set. So again, this is theta 1 component. So before you have a single, in the theta 1 component, you have this Aubrey set, which is the minimizing orbit. But now you double it, you get two copies with exactly the same action. And instead of looking at argument of these two, you look at the following function, u plus, which instead of taking zeta on both sides from the same Aubrey set, you take it from different copies. So u minus c will be zeta 1 of x, u plus of c, which will be zeta 2, where you take zeta 1 from here and zeta 2 from here. Then as a result, what you get is that the gradient of u minus will be this, and the gradient of u plus will be this. Then the remark still work. You're guaranteed to have a homoclinic connection at the minimum of this function. So again, minus sign. So this idea is not new, so it's being used using the Hamilton-Jacobi method to, for example, study splitting of set processes, and then these are exactly those solutions of a Hamilton-Jacobi equation. And you can compute the splitting angle. It will be precisely be the Hessian of this function at the point of minimum. But what the variational method would allow us to do is actually we allow to consider non-transversal intersections, or a priori we don't know whether they are transversal. So what you want to do is you can look at topological intersections. So let me just state something. So this basically goes back to Arnold, and also it's related to the work of Ugo Bessi. So in the case if R is 1 minus cosine theta, it's mu 1 minus cosine theta 1 f of theta 2t, then argmin of UC minus UC plus, which is the guaranteed heteroclinic connection. But it happens to, what happens is that if this function take a global minimum at this point, but it happens to also take a global minimum still at the two oblique sets. So it's a little bit hard to see, but basically the action of going here to itself is 0, but then here you go the full homoclinic. So the argument always contains the oblique set itself, both of them. So what you want to do is that you want to delete those two, which are somehow the trivial part. Then the computation done by Arnold and Bessi is that this argument, this is isolated. Let me just, so it's actually unique. It's a single point, but it suffices to know that it's isolated. So then, as a result, you can prove AC is connected to a C prime if C and C prime are sufficiently close. And let me just draw a picture. It's something like this. The unique homoclinic connection is an orbit like this. And here you basically have A1, and here you have A2. And this orbit is isolated, which means that if you try to move the endpoint, the green orbit always have a smaller action than the white orbit. And now what you want to do, you want to change the asymptotic velocity of this orbit slightly. And it's a non-trivial claim, but it can be proven in this case anyway, that the action is actually continuous in C in this particular case. So since the action is continuous in C, if the action of this plus this with asymptotic velocity C has a minimum in here, then you can change the velocity here slightly, and it will still have a minimum, and it will give you an orbit that actually connect from C on this side to C prime on the other side. So this is the use of this variational method. And one more remark is that this is still true if, for example, the argument is small in a topological sense. So I don't need it to be an isolated point. And it's still true if the argument is small in some sense. This is a little bit technical, but you can say that, for example, you have a contractible open set which contains this, and everything works. So this is the idea that once you get a non-degenerate minimum for this function, then you can always change a little bit. And the difference from, I think, from many geometrical methods is that we do not actually need to study the intersection directly because it always exists. But of course, you need to prove the non-degeneracy. But then we don't have to work on the unstable manifold directly, but we try to prove this using variational methods. So that's yeah.
The delta here has nothing to do with the delta in the statement, or is the same?
Sorry, yeah. Yeah, I need to switch to. Yeah, actually, it was a sigma in the paper.
There are too many letters, so we
Yeah.
should use Chinese letters.
Yes, I will be the first one to agree to that. And then Alain's not here, so I'm not sure who else will agree. So, all right. So this is like a rough idea about how things go. So let me now get a little bit more abstract. So let me make one more remark. So this is what some people call this local diffusion. So once you have something which has non-degenerate homoclinic connection, then you want to say that you can connect to something nearby. But there's a question of shadowing. Suppose you have a family where you both each can connect. Can you actually shadow it? And for this part, I'm actually going to refer to the work of Patrick, and which is based on ideas of mother. So basically what we want to say is I can define equivalence relation such that which implies heteroclinic connection from C to C prime. So this actually is a little bit abstract and technical, so I will not be able to offer much detail on it. So by making this equivalence relation, in particular transitive relation, what this automatically means that if you can go from C to C prime, then C prime to C double prime, then you can go from the first one to the third one. And this is a non-trivial theorem, but what we would like to call it is a variational lambda lemma. So the flavor is a very much like lambda lemma, but with exactly these things play in the role of unstable and stable manifolds. So that's as much I can say about this equivalence relation. So suppose we just take this for granted. So we have this equivalence relation, which allows us to shadow orbit and allows us to chain orbits with heteroclinic connections. What I would like to do, I would like to state two conditions. And what I would like to do is actually use this side of the board because I want to keep them here. So the first one is called Arnold mechanism. And both of these are theorems proven by Patrick Bernard. So Arnold mechanism says that if argmin of UC minus UC plus, as I defined over there using the double cover, so the notation is terrible, so I will not repeat it. Is totally disconnected. So this is a weaker condition than isolated, and it also happened to hold under generic perturbations, so which is why we state it this way. Oh, sorry. You still want to get rid of the other one. If this is totally disconnected, then And this is essentially what I stated over there for this particular example. And the other mechanism, which we'll call mother mechanism, which is actually related to Marianne's talk, because the history is that you have the Birkhoff's theorem for diffusing in the twist map. The mother gave a variational proof of that, and this is a generalization of a mother's proof to arbitrary degree of freedom. So, what it says that if argument of let me cheat a little bit because I run out of notation to use. The theorem, as I state, is wrong, but I think it allows me not to define new things. Okay, so if the Aubrey set is contractible, then so both of these are local connecting results. So for people who know that I actually should have used the so-called Manier set, which is a larger invariant set in general. But in our case, again, we're going to assume the same condition that Marianne assumed, that all the invariant curves have irrational rotation number, and so under these conditions, the set is equal to the Manier set, so it will not cause a problem for us. So this allows me to save a little time in definition. And the point is now coming to a simple remark. The simple remark is if gamma is a continuous curve and either mechanism holds, for all C in gamma, then all C's in gamma are equivalent, which just follows from connectivity. Right, so this is a trivial remark, but we're going to apply it to this curve. So we have the resonance curve, and all we have to prove is that for every single curve, either of these two conditions holds. So either the minimal invariant set is small, meaning that it's a contractible set. This set is a subset of T2, meaning it's a contractible set in T2, or prove that if you lift to double cover, the heteroclinic connections is transversal. So if one of the two holds, then it holds for the entire thing. So that's the goal. So this does not hold for general curve, which is where the normally hyperbolic cylinder for this particular problem will come in. So what I would like to do is I would like to state two properties of this system. So let's call the system H. The first property I'm going to call AM1 because I'm going to generalize it later on, and I'm going to call this property Aubrey mother type. So the first property is this invariant set, which is invariant set for a four-dimensional symplectic map, is contained in the two-dimensional normally hyperbolic invariant cylinder, and is a graph in the cylinder. So it's basically the same picture I've been drawing. So you have the cylinder. So the first property is that it's contained in a 2D cylinder and is a graph. The second property is the following, that let me state it again. This is there were some technical issues. The stable unstable bundle. Oh, actually, let me state a stronger condition. Let me state the following. So it's basically the thing I stated before. Now I'm keeping it as an assumption. So in our paper, we actually had a weaker condition. Basically, we want to say that if the stable unstable bundle, and if you look at the circle here, and you look at the stable unstable bundle, suppose it projects onto the configuration space, meaning your theta component, that would imply your stable unstable manifold is a graph over your theta component. Then we can prove a local uniqueness result. Then it has to coincide with this. So we can actually say this in a weaker way. But here, let me just state it in the stronger assumption. And the point is that once I have these two, then I can prove either of the two mechanisms hold for every single C in this curve for generic perturbation. Here, actually, philosophically, is very similar to Marianne's talk. So the idea is that on a cylinder, the first assumption says that each of these invariant sets has to be the graph inside of the cylinder. So there are only two cases. Either the graph itself is actually a essential invariant curve in the cylinder, or it is not. Now, if it is not an essential invariant cylinder, then it's automatically contractible in T2. So if it is not a invariant curve, then one of the Mathers mechanism would already apply. Now, Marianne would like to use the scattering map to move past any of these invariant curves. And what happens with us is that we would like to look at the family of all the invariant curves in the cylinder, which are uncountably many, and which has unstable and stable manifolds. So you have, in general, a Cantor family of stable, unstable manifolds, and you would like to prove that they are generically intersect transversally to each other. And the word transversal is misleading. We actually require a weaker condition that the intersection, when you project it onto the theta component, is at most totally disconnected. So this is, to some extent, easier to prove in the variational setting for the following reason. So you're basically looking at some property of Lipschitz functions. So these are functions, families of functions. And we'd like to say that argument of this function is generically small. It's not everything. So most part, the minimum is taken on a small set. And this is, of course, true using Sart's lemma if this is smooth family. So if you have a smooth family, then you just use Sart's lemma, then you can get the intersection is always transversal, in fact. But the problem is that this is not a smooth family. It's a family of Lipschitz functions, and the dependent of this is that best continuous. But what we prove is that this family of functions is 1/2 holder in the parameter. And this, let me just remark that some version of this was proven by Cheng and Yan, and my understanding is Zhang also had some unpublished paper involving this problem, and we gave a full proof in our paper. And also, it's a little bit stronger because Cheng didn't prove 1/2 holder. But the point is that as long as you have some regularity, the set of functions for which this bad intersection will happen is of infinite codimension in the space of all functions. Therefore, the bad functions are nowhere dense. So therefore, you know that this kind of intersection, even if it's over a Cantor family, will always be a generic property. And this is why one of these properties will hold. Coming back to why we need these two properties, the simple observation is that if you think of the invariant curves as a family on the cylinder, then they depend further continuously on the parameter which is the area below the curve. It's precisely 1/2 holder. So if you think of the area below the curve as a parameter, then the dependence is always 1/2 holder. And what we basically prove is that the area is actually equal to C because it's actually a symplectic area. So it's the same thing. So, but this you actually need the cylinder, and the fact that the unstable manifold depends also holder continuously on these on this circle. So without hyperbolicity, we will not be able to prove this regularity, which is why we actually also need hyperbolicity for this whole thing to work. So that will be basically a sketch of the proof of this theorem. So let me just use the remaining of my time to say a little bit about what happens in general. So the statement is that we don't really need the system to be actually this. We just need these two conditions to hold locally for the proof to work. So as long as you assume AM1 and AM2, so actually let me say it. Proposition, if gamma is such that AM1, AM2 holds on all C in gamma for a Hamiltonian H. Then the diffusion mechanism hold after what we call a residual perturbation. In other words, there exists a small neighborhood of H on which that the property holds on the residual subset. And what is kind of nice for this is that suppose you have very long gamma. Then you can chop it into many pieces. And on each piece, you prove this property. Then what you get is that this property holds on the residual set in the neighborhood. Now you apply this for each piece. All you needed to hold still on the residual set of a neighborhood is to take the intersection of the neighborhoods associated with each piece. As long as you have finite many pieces, the size of the neighborhood will not go to 0, and the properties still hold on the residual subset of that neighborhood. So the whole thing is that we developed something that is very nicely work locally, and allows us to cut up the whole diffusion path into small pieces and prove each piece individually. And the whole connecting of the global orbit is done automatically for us. And we don't even have to do the perturbation explicitly, as long as we verify this condition on each tiny piece. So that's the main motivation for developing this kind of techniques. And as was alluded to in the earlier talks, at double resonance, you can also build cylinders. And then you can verify those cylinders still satisfy these two properties according to some cohomology classes. Then we can prove that you can diffuse locally a little bit, as long as you can verify this property, as long as you allow an additional small perturbation on a small residual perturbation. So, so just a few more remarks about how this will work. Remark number one is less obvious, but it's crucial for us. So both of these properties are actually at least invariant under symplectic coordinate change, which is sufficiently close to identity. So the reason is a little bit less obvious. The point is that both of these sets can lift to the configuration space, and both of these sets has canonical definition in terms of the Hamiltonian system, as long as it satisfies the convexity property, as our system satisfies. So these things are invariant as long as you keep the convexity. So if you take a coordinate change with sufficiently close to identity, you don't destroy the convexity, then these properties are topological properties of these invariant sets. Under a coordinate change, they still satisfy the same topological property. Therefore, these are invariant. What this means is that we are free to choose whatever coordinate system to work with, because the C is also independent of coordinate change. So basically, we do not have to kind of wrestle with differences of different coordinate change, because this object we work with is sufficiently coordinate independent. And another small remark is that the way I stated these two properties is actually not C1 open, but C2 open in Hamiltonian. But the version I stated for the projection of the bundle is actually C1 open property. So in summary, we have this kind of a property which conceptualize the geometrical structure with connection to the variational structure. But once we have that, then we have this mechanism of just making small perturbations and create diffusion as much as you like, independent of coordinate system, and also relatively robust. So that will be the gist of this construction. And then needless to say, we need to apply it to the general case, which involves a million more details, but I will spare you those details. So thank you very much.